PowerPoint presentation about method and about implementation of that method, maybe about benefit of usage of method also. Some of the slides will be repeated from yesterday, sorry for that, but it is necessary for continuous expose. So contents introduction, the problem very exposed on Belgrade groundwater source. After that theory, or how to say method, iron incrustation mechanism, and after that well elements design or implementation, or how to say benefit out of it. This slide you have seen yesterday, Belgrade water source, and a nice picture really. 100 water wells, 99 water wells along the river Sava banks. Some 40 kilometers of the banks are occupied by lateral wells. You can see it. Yellow spots are water treatment plants. Now this is interesting. Red line is average well possible discharge during the time. We have three periods. The blue one is the number of the wells. At the end, it's 99 wells Belgrade water source. Brown is the yielding of the whole water source. You see, in the time 1986, it was almost 6 cubic meters per second, and today is about 3 cubic meters per second, no more than that. And that means that we have some clogging. What is the problem? The first period, it was period of withdrawal of static reserves, understandable. The second was a period of predominant colmation of the river bed because of suspended matters which come into the river bed together with water. And the third period is a period of screen incrustation and corrosion, and therefore losing of capacity of the wells. Now we have corrosionless materials, no problem with corrosion, but problem with incrustation. Two wells, yielding of the wells, you see one well is with relatively constant discharge, very good, the other well with decreasing discharge, and it depends on the process of clogging. This picture is a picture of lateral inside. Some of bacteria which cause the clogging, Gallionella and Leptotrix. And now one profile, lithologic profile of a water source, part of the water source. You can see how it looks like. And this is interesting. You can see this part which are shown on this picture. Now you have the profile, chemical profile. The discharge of the well is blue. Green is 15% grain size, and the red is 2-valent iron. You see, good discharge means good redox, and also relatively high D50 grain size. In the same time, ferry ion is very low. Where the redox is high, also the ferro ion is very high. Also, it's very interesting, and it shows actually behavior of this phenomena. You can see here the different places where we try to monitor 5 to 10 years disappearance of this phenomena. First one is Belgrade water source, the third, fourth, fifth Danube, and the two is River Morava and the water source by the River Morava. Yesterday's picture, the profile, longitudinal profile of one alluvium, river alluvium. The first part, upper part, mainly oxy condition. You see downstream part, you have mainly anoxic condition and a tiny material. Upper part, very coarse material. Here is the river Sava. It's interesting. upper part of the Sava stream is very oxic, underground is very oxic, 3 to 7 milligrams of oxygen in these aquifers. The medium part is, how to say, oxic, suboxic, something like that, 1 milligram, half milligram, something like that. And the downstream part in Belgrade and around is beyond 0.2 milligrams per liter, suboxic status, very interesting for this phenomenon. How it is going? First, oxidation by oxygen, after that with nitrates, after that with manganese, ferrion, sulfates, and at the end methanogenesis. Phase 1 is the river bottom sediments, and it means intensive sorption potential and high biochemical activity. Phase 2, filtration or curing in predominantly oxic condition. Phase 3, filtration or curing under diminished oxygen concentration or under anoxic condition. And phase 4, filtration under the influence in contact with well screen. Why we lose oxygen? For instance, in Sava River we have 2.5 or something like that total organic carbon dissolved. And it's not enough to reach anoxic situation. So we have actually mineral oxidation. And it is very interesting for the people here. It's not so much mentioned, but very important. This is the same, but another picture, just the same. Now you have iron incrustation mechanism here. You know, 2 valent ions become 3 valent iron because of difference in redox due to biochemical agents. And it happens in redoxes less than 150 or 200 millivolts. And in that case, filter stability criteria for entrance velocity don't work. This criteria was done by German Zichard, Russians Abramov, Gavrilko and Alexeyev, and also Langelier and Riesner works upon chemical parameters for clogging wells, and in recent time first Dubinina, and after that Kulimor, Massa and Hauben works upon it. But what is new here, we try to join ruses of hydraulic head on the water well screen and biochemical reactions, and that is new. Here introduced parameter local hydraulic resistance, that is difference between outside and inside screen piezometric head and entrance velocity, very reasonable parameter. The dimension is time, and it shows the rate of clogging. Now, 7 months after the first slide, now 2 years after the first slide, and now several years after the first slide, we have more and more difference in piezometric head. So local hydraulic resistance become too high, and we have a decrease of well yielding very much now. Therefore, we introduce also a kinetical local hydraulic resistance as a factor which is dimensionless. The both factors depends of contents of iron in the water, redox, granulometric curve, grain size curve, biochemical agencies, nitrates, oxygen, and so on. Out of it, we try to find the relation between critical velocity and kinetics local hydraulic resistance and also piezometric drawdown. And if we say that piezometric drawdown should be less than we want, we would have critical velocity which we can use for designing the well elements. Now something which is a little bit interesting, a relation between 50% diameter grain size and contents of iron in the water. There is a certain relation, not so strict, but there is certain, and it's interesting. It would be better if we would calculate with all grain size curve, but for this circumstance we prepare this. Now it is very interesting. Critical velocity, which means velocity which avoids piezometric drawdown on the filter more than 0.35 meter per year. Velocities under it will not cause more drawdown. And it is very interesting to find out how to design the well elements. Here you have the same, but a little bit more tidy, because we have joined the wells in sections of redox, and you have a blue line. It is a critical velocity due to redox, and red line, it is filter stability criteria. Down you can see some chemical parameters. Brown is iron in the water dissolved, green is nitrates, and blue is content of oxygen. I think that it is very clear for everyone. For instance, Florian understands it well, I think. Yes, and that means high oxygen, high nitrates, low, very low iron or no iron, and the critical velocity is very close to the filter stability velocity. When you go to the left, the low redox, you have high iron, low oxygen or no oxygen, and also at the end of the day, no nitrates. And the critical velocity very, very low. Here is a relation between iron and critical velocity, very important also for designing the well. And what is ongoing research? Correlation between resistance of the screen, water chemism, bacterial species, their activities, types of inner screen incrustations. And how to design the well? First, we have to design proper discharge of the well. It means of the potential of location. After that, establish based on biochemical indicators above all redox and ferro content, the critical well screen entrance velocity, and after that, determine screen elements, screen surface area, number of laterals, and such things. Why it is important? For instance, on Belgrade waterworks, we lose some 150 liters each year because of the clogging of the wells. That means some 6 or 7 million euros each year. And by good maintaining and by changing the well with new laterals, you can spare a lot of money. That's the first. The second thing, you can have a better water source. Very important. Having in mind that in Belgrade water source you have almost don't have pharmaceutics in the wells, so quality of the well water, rough well water, much better than the quality of the water taken from Sava River and treated. Here is one sketch about well elimination design. You have a first piezometric line or water table, and after that down you have piezometric head on down aquifer. You have one interlayer, or let us say aquitard or something like that. And to find out what is potential of this well or this future well, you must find out the nature of colmated river bed, permeability of it, and also the difference between horizontal and vertical coefficient of permeability, or coefficient of permeability of horizontal aqueduct. Aqueduct should be clay aqueduct, or maybe even calcrete aqueduct, or something like that. Equations are well known. Here, very important boundary conditions to the laterals. That's very, very good. This man will talk a little bit about that, I think. Mathematicians, rise up hand, okay. And now you can see the position of one well, RB16, Belgrade water works. Schematization, you can do it more detail or less detail, and to try what is difference. For making a good model, 3 proposals necessary. First, enough good data. Second, good head of engineer. And third, good mathematical model. 3 are very necessary, especially second one. This is some of results. Piezometric head difference between lower and upper layers. That's very interesting because out of it you can find what is vertical permeability. Right percent of varies feeding of the water well. It is interesting to know when you are talking, or when you are concerning how to say transport of undesirable material to the well. So such things sometimes can be useful. Time zone of groundwater travel through the semi-permeable interlayer, also for the same purposes. And now something which is relatively interesting. Well laterals and intensity of velocity incoming to well laterals. So at the top of laterals, at the beginning, the velocity is the biggest. After a time, it moved toward the water shaft of the well. Now we will compare 3 wells. It will be interesting because they have different chemical constitution and different grain size distribution and different redox. So therefore, you can see them here. RB46, lowest redox, and so therefore lowest entrance velocity permitted. RB8M, little bit better. RB16, little bit better than RB8M. When we see diagram with iron, we see that the best is RB16, some 0.6 iron, RB8M a little bit above 1, and RB46 almost 2 milligrams of iron. And what is result? RB16 now have 81 liter per second extracted. It is possible to extract 120. And what should be entrance velocity, you can see here. So to do it with 120 liters, it's necessary 185 square meters of lateral surface. That means 4 or 6 laterals. RB46, now 22 liters per second, can be 55, no more. And 275 square meters of laterals, 6 or 8 laterals. Too much and too expensive for so relatively small benefit. RB8M, now 35, could be 90, and the surface necessary 281, that means 6 or 8 laterals. In this moment, for waterworks is the best to make a new drains on RB8M because the benefit of 50 or 60 liters per second is payful for this amount of money which should be done to do that. The method is significant in technical and economic terms and very new now, very new, for the development of water supply sources based on bank filtration in suboxic and anoxic environments. The method is new and only partly reported, even today. A lot of space remains for scientific research on the correlation between water chemism, grain size distribution, and mineral composition of sediments, the biochemical agents, well incrustations, hydraulic losses, and the well screen. That's relation are important. Who wants to think about that? Also, mineral oxidation in alluvial aquifer, very interesting. That's it. Thank you very much.